Chapter 9. Fractionation. This chapter covers the Polybius square, splitting a letter into smaller parts, such as bits or hexadecimal digits, mixing and recombining those parts. The first two basic tools of cryptography are substitution and transposition, which are covered in chapters 5 through 8. The third fundamental element of cryptography is fractionation. This means breaking the normal units of language, letters, syllables and words into smaller units and operating on those units. The smaller units are commonly bits, decimal digits, hexadecimal digits, or digits in other number bases. This chapter covers fractionation using digits in bases 2, 3, 5, 6 and 16. Plus some other forms of fractionation. Section 9.1. Polybius square. Possibly the oldest method for representing letters as smaller units is the Polybius square, which we saw in section 4.4. Here each letter is represented by two base 5 digits, making 25 possible two-digit combinations. The Greeks did not have a representation for 0, so their digits started at 1. Here is the Polybius square from section 4.4. Each letter is represented by its coordinates in the square, that is, by its row and column numbers. For example, the letter P is on row 2 in column 5, so it is represented as 25. When needed for clarity, this can also be written as 2, 5. A Polybius square by itself can produce a number of different ciphers. For example, it can produce a simple substitution by replacing each letter in a message by the letter to the right in the square. U becomes V, or below, U becomes Z, or below and to the right, U becomes S, or left, U becomes P, and so forth. This idea can be extended to a polyalphabetic cipher by changing directions, say right, left, down, right, left, down, etc. You can also go 2 letters away or use knight moves as in chess. A Polybius square can also be used to produce a Polybius ripple cipher. Begin by replacing each letter of the message by its coordinates, simply written out in one line. Starting with the second number in this list, add the previous number to the current number. If the sum is more than 5, subtract 5 to keep the numbers in the range 1 to 5. Then turn these numbers back into letters using the Polybius square again. The Polybius ripple cipher is rated 3. The cipher can be strengthened by using a different Polybius square for converting the coordinates back to letters. Let's look at a few hand ciphers from the 1800s based on the Polybius square in sections 9.2 to 9.7. I cover some additional hand methods in sections 9.8 to 9.11. Then I discuss some computer methods in the rest of the chapter. Section 9.2. Playfair. The Playfair cipher was invented by Charles Wheatstone in 1854. Wheatstone is well known among electrical engineers as the inventor of the Wheatstone bridge, which measures electrical resistance. Wheatstone and William Cooke invented the needle telegraph several years before Samuel Morse invented his key telegraph. Cooke commercialized the needle telegraph in England years before Morse began his telegraph company in the US. Wheatstone's cipher is called the Playfair cipher because it was Wheatstone's look-alike friend, Baron Lyon Playfair, both had bright red hair and stood about 5'2", who advocated for its use and convinced the British Foreign Office to use the cipher for diplomatic communications. Historical aside. Since this cipher was not called the Wheatstone cipher, that left the Wheatstone name available for a second cipher that Wheatstone invented circa 1860 and exhibited at the Paris Exposition Universelle in 1867. The Wheatstone cryptograph, which resembled a large pocket watch, consisted of two stationary concentric rings made of stiff cardboard and two movable clock hands connected by a simple clockwork mechanism. The inner ring was erasable and could be changed for each message. This ring had the 26-letter alphabet in scrambled order, while the outer ring had the standard 26-letter alphabet plus a blank, making 27 positions. You move the long clock hand to indicate the plain text letter on the outer ring, and the short hand moves to indicate the ciphertext letter on the inner ring. When the long clock hand completes one revolution of 27 positions, the short hand also moves 27 positions, which is one complete revolution plus one extra letter position. So the shorthand starts from a different point on each revolution. An equivalent device with movable rings and no hands had been produced by Colonel Decius Wadsworth, Chief of Ordnance, in 1817, based on plans made by Thomas Jefferson in 1790, but it is Wheatstone's name that is forever associated with this concept. Photo provided by Ralph Simpson. The inscription reads, "The Cryptograph. C. Wheatstone, Inventor." The Playfair cipher is based on the Polybius square and enciphers 2 letters at a time. That is, it enciphers bigrams. The square can be prepared by mixing the alphabet using any of the methods of section 5.2. One low-frequency letter of the alphabet, such as J, Q or Z, is omitted to make the alphabet fit into a 5x5 square. In French, J, Q and Z are common, so omit W. In German, omit Q, X or Y. When the omitted letter occurs in the message, some other letter is chosen to replace it. In our case, each J is replaced by an I. The next step is to divide the message into bigrams, for example, M-E, E-T, M-E, T-O, M-O, R-R, O-W. If a bigram is a double letter, this should be broken up, typically by inserting an X in the middle. This is a good reason not to omit X from the square. Also, if the message contains an odd number of letters, an X is added at the end. The message becomes MEETMETOMORXROWX. We are now ready to encipher it. Playfair has 3 rules. 1. If the 2 letters are on the same row, each letter is replaced by the letter to its right. 2. If the letters are in the same column, each letter is replaced by the letter below it. 3. For all other letters, each letter is replaced by the letter in the same row, but in the column of the other letter of the bigram. It is understood that the square wraps around, so in the square in section 9.1, the letter to the right of Y is U, and the letter below Q is W. These rules can be restated in terms of the coordinates. Let the bigram we wish to encipher be R1C1, R2C2, so that the first letter is on row R1 in column C1, and the second letter is on row R2 in column C2. Now the 3 rules become: 1. If R1 equals R2, then substitute R1 C1 plus 1, R2 C2 plus 1. 2. If C1 equals C2, then substitute R1 plus 1, C1, R2 plus 1, C2. 3. Otherwise, substitute R1, C2, R2, C1. Let's encipher our sample message, MEETMETOMORXROWX, and see how these rules work. The first bigram is ME. M and E are in different rows and different columns, so Rule 3 applies. M is in row 2, column 4, and E is in row 3, column 2. So M gets replaced by the letter in the same row, namely row 2, in the same column as the letter E, namely column 2. The letter in row 2, column 2 is S, so M is replaced by S. Likewise, E is replaced by the letter in row 3, column 4, namely C. In the same way, ET is replaced by DO, and the second ME is replaced by SC. The letters T and O are in the same row, so Rule 1 applies. They are replaced by the letters to their right. T gets replaced by N and O gets replaced by Q, so TO is replaced by NQ. MO goes by Rule 3. It is replaced by SR. R and X are in the same column, so Rule 2 applies. RX is replaced by XM. RO and WX both use Rule 1 and are replaced by TQ and XY. The entire message thus becomes SC, DO, SC, NQ, SR, XM, TQ, XY, which is SCDOS, CNQSR, XMTQXY after regrouping. Here are some diagrams to help you visualize how the bigrams LY, TO and RX are enciphered. The Playfair cipher remained in military and diplomatic use until at least 1960. Next, let's take a brief look at how a Playfair cipher can be solved.